Hello, I'm calling this tutorial Intermediate Finite Element Analysis in NX. So I'm going to start with just a really simple block. It's just an inch on each side and then 4 inches long, so it's a nice square inch, so the stresses will be easy to compare to what we know they should be since it's a square inch. I'm going to use several different meshes, including mesh adaptivity, and then also show how to do a thermal analysis in this. So I've already got the part drawn. It's something that you'll be able to very easily draw yourself. I'm going to go into advanced simulation. The first thing I'm going to do is go through some different types of meshes. So you should get a window if you haven't created anything yet, creating a solution. I'm going to go ahead and create a new one. So you'll get the window though, but since I already have some solutions here for this, I need to go over here and right click, and I want to do a new model and simulation. I last used thermal, so I want to make sure I set this to structural, and I'm just going to use the NX Nastran solver. Everything else should be good. Okay, so I'm going to keep it with linear for now. You could change it to linear. It doesn't really take that much longer to solve, especially if you're at very high stresses, anywhere close to where it would be nonlinear, which is probably most of the time. But linear is okay for what I'm doing. But again, most of the time, probably wouldn't be a bad idea to go ahead and pop it over to nonlinear and do things. It doesn't really take that much longer at the end of the day. So I'm going to leave it in linear. I'm going to create a mesh. So I showed how to do a 3D tet mesh in previous FEA tutorials. So I'll get to that in a bit. I want to add mesh adaptivity to that. I want to show how to do a 2D mesh though. So for a part like this, if this was a solid part, I'd want to definitely do a 3D tet mesh or a swept mesh. I'll show how to do a swept mesh for this in the thermal part. If this was actually just a piece of box tubing, so a box square tubing, and it was thin wall, 16 gauge or something like that, and I just drew it as a solid just to make it really easy to draw. But whenever it comes to FEA, I actually want to mesh it as if it was a 16 gauge steel tube. I can do that. I don't have to actually draw the cross section and then try to figure out how to do a 3D tet mesh with that. I can basically do a 2D mesh along all of the edges of it, and it actually works out quite well. So what I'm going to do, I want to select the edges that I want to mesh. And I'm going to go ahead and mesh the end caps of this. So this would be like there was a plate welded on the end of this. So this would be hollow. I do have to set the thickness of it. It's kind of strange how you set the thickness in NX, so I'll get to that here in a bit. But let me get a mesh. So I'm going to use 1/8 of an inch. That seems pretty reasonable for this. I'm going to hit OK, and I've got a mesh. So since it doesn't go through the depth, it's just really quick to set this up. Okay, so before I do anything else, I want to make sure that I set a material. I always forget to do that. So I want to come up here, assign materials. I'm going to pick the body, and let's just do 6061. Okay. Now I need to set the thickness. So you need to come up here to physical properties. You need to select the mesh, and if you have multiple meshes, they'll all be in here. It's not very descriptive, but since that was a shell mesh, and I can click and it shows the mesh, that's what it is. So I can click the gear, or the wrench, or I can double click hit up here, and I get this dialog. Here you can set it to plane strain if you want to do plane strain. And you can see the material inheritance. Here's where I need to put thickness in though. So I want to go ahead and just call it 16 gauge. So we've got 65 thousandths of an inch. You can see some of the other options here as well. You need to know a lot more about your material to get into this. But I'm just going to leave that okay for now, just setting the thickness and closing it. And now I have a simple 2D mesh. So in order to load it, I'm going to go into simulation. I want to do a constraint. I'm going to simply fix one end of this thing and then just apply, let's just give it a tension for now. Force that end. Let's see, let's put something quite large. So let's put 2,000 pounds. We'll probably get a decent force from that. I need to make sure I pick a vector, and I do one in tension, so that looks correct, and there we go. Okay, now I should be able to solve this and get a result, and it'll be really quick. You probably won't even see the solver window. Yeah, it's already done. Very small number of elements compared to a 3D tet mesh, so it solves super quick. Okay, so I want to go to my results, I want to check, let's do elemental nodal so I get the blend. And you can see the strain's exaggerated. And if I had, so I put 1,000 pounds force on it, what it does is it takes that force and it divides it by all the nodes and then applies it to the nodes. Since these nodes around the perimeter are supported by what would be the edges of this box tube, and this would basically be like a 16 gauge plate welded onto the end. If I put that load distribution even across, then yes, I would expect it to kind of balloon out like that. So that deformation makes sense. It is exaggerated. Always remember that this is exaggerated. In no way would it stretch that much in the real world. Stresses, we're talking about, let's see, somewhere here. So let's get a number. So I can do identify results, and I can just pick that. And it's about less than 8 KSI. So this would be perfectly fine out of any kind of steel. Out here, we're talking a lot bigger number. So that's going to be 59 KSI, I believe. So depending on what kind of steel, it may or may not be okay. And then certainly in the red, it needs to be pretty serious stuff. But it's kind of a strange loading situation. This would be, I guess I could treat it as a pressure vessel, but I probably would use a different kind of load. I'd probably use a pressure instead of a force. But they end up being the same thing if you calculate the surface area for it. But so that's just a really simple shell mesh. This is really helpful for doing tube frame structures like space frames. Most things are just simple cross sections, and it's really easy to do. For anything that's thick, you really can't do this at all. I mean, so where does that point end? Probably somewhere around 1/10 of an inch is where I would, or just very complicated geometry. I'd probably switch over to doing a full 3D TED mesh. It really depends on the resources you have. A properly done 3D TED mesh it's almost always going to be better, assuming you have a small enough element size. But you're going to get to a point for certain structures where you just have too many elements and it won't solve. So there's really no harm in trying to start with this because it's going to solve quick. And as long as you're dealing with certain thin wall structures, this actually works quite well. So really simple 2D meshing, but again, thick parts, really complicated, strange parts, it starts becoming an issue. So I'm going to go back, and what I'm going to do now is show how to do mesh adaptivity. This is something that once you know how to do it, you're pretty much going to do it anytime you use a TET mesh. I would use adaptivity because it basically gets rid of the whole trying to do a mesh sensitivity analysis thing. It basically does that for you, and it does it a little bit more intelligently than just cutting the mesh size in half and then solving it again. So it's kind of hard to get to in NX. I don't know why they hid it, considering it's something you should probably use almost every time you do an FEA. So I'm going to go back to meshing. I'm going to go ahead and delete this mesh so it's not in there causing a problem later. So I'm going to go into the finite element model, and then I'm going to go to the 2D collector. I'm going to find that thin shell, and I'm just going to get rid of it. So now that's gone. I believe if you go into physical properties, yeah, the property is still there, and it's just kind of orphaned. It doesn't do anything, so I could delete that. Close that out. Don't have to do that. It's just going to sit there and not do anything if you leave it in there. It's probably NX should clear that out, but it's not hurting anything. So the loads and the constraints are fine. I don't actually need to change those. Those are based on the geometry of the part rather than the mesh. They get mapped to the mesh once you actually have a mesh. So to do adaptivity, you have to have a 3D TET mesh. It doesn't do it for anything else. So 3D TET mesh, let's just keep that 8th. I like that. And then put it in there. And the only difference between this, it's going to look exactly the same because you can only see the outer surface. But it's inside meshed all the way through with the 3D TET versus the 2D external. So now I have a 3D mesh. Is it fine enough? Is it coarse enough? I don't really know until I start running it, until I do a mesh sensitivity analysis. So what I want to do is actually have NX run this FEA, get the results, refine the mesh, run another FEA, compare the results, check for a % error, and keep doing that for a number of iterations or until it gets to a % error that I'm happy with. So to add adaptivity, it's okay, so you have to be in simulation, I believe, and then menu, insert, adaptivity setup. You get this little dialog here. You can name it stress percent error. So let's say I want, I know for this structure based on history, if I set it to 1%, it's already fine with this mesh. This mesh is good enough because this is really a simple part. But if I set it to, let's do 0.25, it'll take a few iterations to get there. And then, so I'm not going to change the error deviation. This max iterations, you need to set that to some normal number. If you set it to 1,000, you might have something that sits there and runs forever and doesn't ever really converge because it just can't get to the error you need. So 3 is fine. I might need more. We'll just see what the solution looks like. Minimum element size, you probably need to have something in there. So otherwise you start getting elements that are really small. So let's say a thousandth of an inch is as small as I want to get with an element, which is quite small. It's probably too small for this, but with only 3 iterations, I'm not too concerned. So, okay. Now, there's a trick you need to do to make sure it actually solves correctly. So if you just solve, it's going to try to solve this solution. I actually need to right-click on this setup and solve it. You don't get all of the solution information that you would get if you just did a regular solution, so you pretty well have to just open or just make sure you can see this information window and watch it as it goes through the solution. So this is going to take a little bit of time, so you can see it's doing the initial solution. Initial error, so 0.5% or so, and my target was less than that, so it's going to refine the mesh. And you can't see it because my window is covering it, unfortunately. But what it's doing is it's actually shrinking. You can see some of the elements down here where that constraint is have gotten smaller. It basically subdivides the tetrahedral mesh into smaller tetrahedrons, and then it redoes the FEA, and then it will automatically calculate the percent error, and it'll do this for every iteration. So it's very helpful. It's not the end all be all of FEA. I can't just run this and exactly trust the results, because what you'll find in this particular situation, so you can see now it's a little bit better, and you can actually see the refinement here, is it's going to keep refining and refining and refining because of the way this fixed constraint works here in the practically loaded part. You're going to end up seeing little bitty peak stresses somewhere in here that are really ridiculously high that you really can't rely on. It's just because that in the real world you never can get a constraint that works exactly like this. So it's going to start refining away here, but just right away from those really highly loaded nodes, which is what you'll see here in a bit, everything else is going to be almost exactly what it's supposed to be, which is the load basically divided by the area in square inches. So for something like this, it's really not even necessary, of course, because it's such a simple structure. But for any real 3D part, I mean anything of any real complexity that you need a 3D TET mesh on, I would absolutely use adaptivity on it. And it just gives you some idea about what your percent error is and how you need to refine the mesh. It's pretty well necessary for any kind of real analysis is to have this kind of mesh sensitivity. So I think, yep. So it did it. I hit it on the second iteration. I'm going to go ahead and close that. So I have less than my 0.25% error. You can see how it refined the mesh. I'm going to go into the results down here. Oh, I need to actually double click on that solution, not the setup. And that actually tells you the error if you want to see what the error looks like. Stress elemental nodal. And you can see it's a very even. I put 2,000 pounds on it, didn't I? So I can really easily verify that. So let me, actually I need to, just a second. I just noticed that it's not giving me the correct toolbar up here, so I don't have the tools for checking the mesh and checking the results and graphing it. So I figured out a way to fix it real quick, though. All I really need to do is to go back to the simulation, open up my previous results case study, and then it puts the correct menu bar up. And now I can come back in and to the navigator and do these, and I'll get the bar up here. That's probably an NX error. It doesn't switch the toolbar when I go to these results. So now I've got the tools where I can actually kind of dig into this and see what each nodes look like. So identify results, I can just click through there, and I get 1002 KSI, so which is what I expect from that load. And it gets a little interesting around here, and that's what I was talking about. You get to these edges, and you get this kind of artifact here that if you keep refining, it's going to keep getting higher and higher and higher right at these corners. And it's really, I guess that's a stress concentration. So it's, would I really be that concerned about that 7 KSI? Probably not. Would I really want to adapt the solution much more now? I mean, I'm down to a low enough percent error that I'm pretty happy with this. But again, it's just something stupidly simple, but it's really easy to validate because it's a square inch. So, but for any arbitrary complexity, you could do this, and it's much better than trying to just cut the mesh size in half. It's much more efficient with your time too. So that's mesh adaptivity. Of course, if I want a graph, I can create a graph and pick some line of nodes across that and get a nice graph across it. It's not really helpful for this, but adaptivity, very powerful thing. So something you should definitely use regardless of what kind of FEAs you're running. If you're using a TET mesh, I would use some kind of adaptivity. Okay, so what I want to do next is I want to do a thermal analysis for the same part. This is something I haven't talked about at all. So I want to come back to, let's see, I'm going to go ahead and I need to get a brand new solution created, so I actually need to get back to the part, I believe. Okay, so what I need to do is go to the session. I'm going to double click that. That gets me my block. Right click, new FEM and solution. So it's going to be 4 in this. Now I want to set the analysis type to thermal. Everything else looks good. Okay. So the process is almost exactly the same. It's just the loads and constraints are fluxes and temperatures instead of forces and kinematic constraints. So thermal, note that it's already nonlinear to start with. This is you can do a steady state or a transient. It just depends on what you're doing. Let's start with steady state. That's the easiest one to do. So steady state, default initialization temperature. You might set that to the room temperature wherever you're working. Okay. And what I want to do is I need to create a mesh, of course. That's always the first thing that you have to do. So I don't know why it didn't take me into meshing, but I'm going to come up here and activate meshing. So I'm going to use a different kind of mesh than anyone that we've covered. I'm going to use a 3D swept. I like these in general for shapes like this that are kind of a swept profile. You get a nicer mesh. This is really important if you're doing CFD analysis, which we can't do CFD in this, but you're going to use swept meshes for any kind of CFD if you can. I mean, sometimes you can't. You have to use a TET, but especially for things like analyzing turbine blades, you're always going to use a swept mesh, and you have to use your boundary elements as necessary. But doesn't really make that much, you don't have to worry about that kind of stuff for a thermal analysis, but I am going to use a swept mesh just to show you how to do it. So we're going to use an 8th. I'm going to pick this face, and it's going to grow, it's going to basically start here, mesh this face, and then sweep it along the part, and it makes this really nice mesh. So no, it looks just like the 2D mesh, except this actually extends through. So this whole thing is basically mesh with a bunch of little cubes. So nice, even, consistent mesh. Sometimes it works, sometimes it doesn't. Depends on the geometry. For anything like this, it's a nice extruded or swept part. It works perfect. For really arbitrarily complex 3D parts, might not work that good, but I like it for this. Okay, so I've got that mesh now. It is a 3D mesh. I don't have to set the thickness. It goes all the way through to the depth of this part. I need to go into simulation. I need to put constraints on. So I can do convection. I can do a thermal constraint, so let me do a thermal constraint. I'm going to take this wall and I'm going to say it's stuck at 250 degrees Fahrenheit. I'm going to put a flux on this wall, that would be a load, so heat flux. Uniform element, you can change all sorts of different settings here. I want to set BTUs per second squared. I do not like BTUs as a unit, so let's do watts per square inch, and let's put 100 watts into this thing per square inch. And okay, so now we've got heat going in, we've got temperature here. Let's do a convection constraint. So I'm going to pick this face, ambient temperature, 75 degrees, convection coefficient. I do not have this. So watts per millimeter. Actually, I'm just going to make a number up for this because I don't have a chart handy. watts per square inch per C. Let's say 10. So obviously you'd have to know this. I mean, it depends on what your convection medium is, how fast it's moving, and all sorts of other things. So you pretty well have to have heat transfer to even understand how to calculate this number or get this number. So that is an input that's required. But now I've got a convection on that face. These other faces are just set to the base temperature. So now I'm going to, so that should be good. Oh, actually, I need to set a material. I always forget to do that. So back to meshing, assign materials, select the body. Let's go back to 6061. Okay, back to simulation, solve. Okay. It's going to churn on this for a while. It should be pretty quick because there's really not that many elements. Since it's nonlinear, it does have to do a little bit of iteration. Wow, that was really quick though. Close, cancel, results. Down here, note I get some things up here from previous solutions. So let's do temperature nodal scalar value, and I get this nice chart that kind of looks like a FLIR image. It's kind of nice of them. So 250 here. Note that that would be where the temperature comes in, so you can see it's a little bit higher here, and then you can see on my convection side, I believe that's this side, that's a little lower. So that's just like FEA for structural, just incredibly powerful. I mean, if you're designing heat sinks, I mean, you can do all your thermal design for heat sinks here. So very, very powerful tool. You still have to do your mesh sensitivity. So if you want to do the adaptivity, you've got to do a 3D tet mesh, or you could do the sweat mesh and make it smaller and see what it looks like. But that's how to do a thermal. That's how to do mesh adaptivity. That shows you some different mesh types. So I think that's it for this tutorial. All right, thanks everybody.